Hi, thank you, Louis. This is Joel Rooks with Siemens. As a brief introduction to myself, I am the National Account Manager, so I manage the Siemens activities at NASA. And I've been with the company 24 years and been focused most of my time on working with NASA. I'll have John Frederick introduce himself at the start of his presentation portion. So I'm going to give you guys a brief introduction to Simcenter 3D, and then we will go in and talk about using our Space Systems thermal product and working with 3D boundary conditions and doing data mapping. And JF's going to show you how easy it is to do that. And at the end, we'll have a technical wrap up and question and answers. Next slide. So what is Simcenter? I think a lot of you have heard of NX before, and NX is a fully integrated CAD/CAM CAE system. Simcenter, the product line, was introduced in June of 2016, and Simcenter 3D includes all the capabilities of what was called NX CAE before, new capabilities. Next slide. I think you skipped, did you skip one, JF? Yep, that was actually the next one. So I guess we're in reverse order. So let's do that one and we'll go back. So one of the reasons Siemens launched Simcenter was because our simulation portfolio had grown rapidly through organic growth and through acquisitions. And you can see through the slide how we've been acquiring several companies through the years, and we really accelerated our acquisitions in the past 3 to 4 years, especially in the simulation area. And so this slide does show our CAE heritage. And one of the key aspects of this slide is that Maya, who develops our thermal software, has been working with us and developing products for Siemens since 1983. So they're a key part of Siemens' strategy for simulation. Next slide. Thank you. So there are three main pillars of Simcenter. We're going to focus today on the center one, the CAE simulation, but we also have on the top there system simulation suite of products, and we also have physical testing. So if you want to do actual testing and correlate that to your final models, we can do that. And all of this is managed through our Teamcenter PLM system. We can also do multidisciplinary optimization through HEADS, which will wrap all these products shown and others. And we'll be showing HEADS at a later session today. Next slide. So Simcenter has a very broad suite of solvers available, including Nastran. Today we'll be focusing on the thermal aspects and showing our Space Systems thermal system over on the far right. And all these can be accessed through one common user interface. So let's show it to you. Over to you, Jeff.
Thank you, Joel, for the introduction. So, so my name is Jean-Frédéric Bruel. I'm an application engineer that works with Simcenter 3D. I do both thermal and flow simulations mostly. And so today we're going to look at Simcenter 3D Space Systems Thermal, but technically what we're going to show today is accessible to all the different solvers inside of Simcenter 3D. And so before we go to the software, let's take a little bit look in the past a little bit here. What you see on the slide here might be familiar to some of you. Some good old Fortran that you had to code up to do some interpolation schemes or user subroutines or input cards directly into the solver in order to be able to interface with maybe temperature fields or heat transfer coefficients coming from other codes that you want to run as boundary conditions on your model. So instead of, and this might not be that long ago. You might still be doing this today. It's quite, it takes a lot of effort. It's quite error prone. Today, we have a much better workflow for you by using Simcenter 3D. In Simcenter 3D, you have integrated user interface for 1D, 2D, 3D, and 4D fields. You can view those fields directly in the UI. It looks something like this image. You can see all the Cartesian coordinates with the heat transfer coefficient directly. You can also graphically display these fields either as a 1D or actually probably more of a 2D or 3D plot like this one here. Or you can also display the Cartesian field spatially using different types of icons with color gradients, which lets you visually inspect your field, make sure you're working with what you think you are before ever solving the model. So this is before the interpolation. This is the raw data that you can look at, but we can also look at the interpolated data directly on the mesh as well. And that's all done upstream in the preprocessor that is Simcenter 3D. Now, if you're hand coding a Fortran subroutine to do this, or if you're using the solver input cards, you usually only have access to 1 or 2 interpolation methods. In Simcenter 3D, we have access to all these different interpolation methods that are quality tested every release. So you're sure that they are giving you accurate results every time. They're not, they're bug-free. You know, they're quality tested every release. Depending on the number of variables you have, some of them are available or not, depending on the scheme. Why would you need to do this? Some examples would be, for example, you have high-speed flow fields and you have adiabatic wall temperatures that you want to apply on your thermal model. You have some radiative heat fluxes that aren't taken into account explicitly in your model that are coming from a different type of model, and you want to just apply as a heat flux on the surface of your spacecraft, for example. Or you could have gas temperatures and heat transfer coefficient distribution over the surface of your spacecraft. You might also have convective heat fluxes coming from exhaust plumes from motors and things like that. There's plenty more examples out there for different physics that you could use what we're going to be showing today. So so the advantages to using Simcenter 3D for this is, as I mentioned before, you don't need to code anything. It's all out of the box functionality. It's integrated in the UI for Simcenter 3D. Since you're not coding anything, you're saving a bunch of time. It's quite easy to use, and you have graphical checking of your data. So before even running your model, you can say if your data is right or wrong, or if there's any problems with your interpolation scheme. We also allow for different unit systems to coexist in one model. You can use imperial units for one field and SI units for another if you like to do that. You can also switch between units quite easily. We'll look at that in the demo in a couple of minutes. We'll also, you're also able to import data from comma-separated variable Excel sheets as well as text files. So you can get data from pretty much any other simulation tool out there into Simcenter 3D for your base simulations. And all these things make for a very reliable process, since you're using quality tested interpolation schemes, you're graphically checking your fields, and you're not coding anything, so you don't have to fix bugs in your own code and relearn Fortran if you're like me. So enough PowerPoint. Let's jump into the software. And today we're going to be working with this oddly shaped spacecraft. I was tired of using the good old cube example model, so I had a little bit more fun. What we're going to be simulating here is, let's say this oddly shaped spacecraft has to fly through atmosphere. So I have one of my colleagues that ran CFD analysis on this. So I have a field of heat transfer coefficients that vary with Cartesian coordinates that I want to apply on the surface of the spacecraft. So I am going to create a convection to environment constraint on the entire surface of the spacecraft. And I'm going to go and create a field table where the dependent domain is a convection coefficient, and my independent domain, in this case, would be a Cartesian coordinates. But as you can see in this dropdown, we have many different variables that you can use as your independent domain. We just happen, for this example, to be using Cartesian. We next will import the data directly from a comma-separated variable file. And here we go. This is the data that was sent to me from that CFD analysis. Right now, I know for a fact that the units in that file are actually in watts per meter squared, so I can switch those quite easily. But let's say I'm more comfortable with British or imperial units, and I want to make sure these are actually in the right range. I can simply go here and convert those into BTUs, for example, and then I can have a better feel for if those values are what I'm looking for. Now, personally, I much prefer SI units, so we're going to go switch back to that for the remainder of the presentation. Now we've applied that heat transfer coefficient on the surface of the spacecraft. We've looked at the field in spreadsheet format, but it'd be nice to be able to view it graphically. And so we can simply do that by turning on this check mark, and this is the raw data of the heat transfer coefficient simply floating in space right now. However, what the solver is going to get isn't this exact field. It's going to be interpolated values from this field onto the mesh. And so what we want to do is to make sure that the raw data that I have here is going to be correctly interpolated on my mesh. And so we can simply compare in Simcenter 3D the raw data with the interpolated values on the mesh. So let me simply change the units here, and we'll look at the scale for the raw data here. So immediately we can see that let me bring up that color bar again. There we go. So we can see that the min and max for my raw data is 109 and 6. Meanwhile, for the interpolated data, I only goes to 90 and 10. So there is definitely some clipping going on. It's not quite accurate. We can change the scale here to make a better comparison. 10.98 and 90.26. And so we can see that mostly it seems like there's a lot of clipping going on in this region. That's fine. I'm only using the default interpolation scheme here. I'm not actually using the, there's other interpolation schemes available to me. And we can compare both interpolation schemes really easily. What we'll do is we'll clone this field and we're gonna edit the options and change the interpolation scheme. So by default, we were using Delaunay fast. However, let's try nearest neighbor as an interpolation scheme for this data. And now to see the data on the mesh, I'm simply going to go ahead and apply it once again in a convection to environment boundary condition. Simply change the field here. And now we'll be able to compare them side by side. So on the left, we're going to be putting the Delaunay interpolation scheme. And on the right, we're going to put the new nearest neighbor interpolation. And let's change the units. So straight away, we can see that the nearest neighbor is much closer to the raw data, at least at the min and the max. And so for this particular model, with this particular mesh and data, nearest neighbor would be the interpolation scheme I would go for. But we also have other interpolation schemes we could try. There's at least 4 more in the list there that we can compare, and each of them will have their their strengths and their weaknesses depending on the type of data that we're interpolating and the type of mesh that we're using. Now, this is a fairly simple example. It's a simple heat transfer coefficient varying over a surface with a constant bulk temperature. But let us say instead of applying a single temperature, we actually have a varying temperature, fluid temperature on the surface of the object. We might want to apply instead a heat flux, where we will take a heat transfer coefficient and multiply that heat transfer coefficient by a delta in temperature, where the delta in temperature would come from the surface of the object temperature minus a fluid film temperature. And that's entirely possible, and that's what we'll do next. First, we'll create a new field for our temperature varying Cartesian, or temperature that is dependent on Cartesian coordinates. So our dependent domain is temperature, and our independent domain is going to be Cartesian field. And now we will once again import that data coming from another software or another analysis. This time we're going to be using a text file instead of a comma separated value file. Here we go. And now we have that temperature versus Cartesian coordinates field, and we can now apply a heat load, or a heat flux to be precise. The way we are going to do this is to use the FD function. So the FD function is a symbolic expression that is understood by the solver at runtime, and it calls a field to be evaluated. So we're going to call first our convection coefficient field. And coefficient. And we want to multiply that by temperature difference. So we want to use the temperature of the surface. To do that, we will use the symbol-like expression temperature, which is an expression that gets evaluated at runtime. So this will change as the run evolves. The solver will understand that to be the element temperature that you're selecting, minus the field that we just imported. So once again, we'll use the FD function to call that temperature versus Cartesian field that will get evaluated at runtime by the solver. And one last. And we also need to apply it to the surface. Oh, typo. Oh, I'm missing. Sorry, I'm just, it looks like I made a mistake in my formula. Oh, quick. Okay, let's type that again. FD, sorry about that, convection coefficient. So heat transfer coefficient times the delta in temperature minus our field. Here we go. I don't know what I typed wrong last time, but it must have been a small typo. Sorry about that. So now that we have that formula in, so we have our heat transfer coefficient that varies with Cartesian times a delta in temperature, which is the surface temperature evaluated at runtime, minus our field that is varying over the surface of our spacecraft. Now that that field is entered, let's make sure, because we just saw I make plenty of mistakes when I type things in, let's make sure I didn't make any mistakes by plotting the contour for this field. Now, instead of being a single value, this is actually a temperature-dependent field now, in addition to being Cartesianly spatially varying. So we can actually vary the temperature of our surface and see how that affects the heat flux being applied on our surface. We can do a static plot, or we can even do an animation. So I could animate the heat flux changing as the temperature of the surface changes from 0 to 100 degrees Celsius. Like this, for example. So for these types of fields, oftentimes making an animation is a lot more telling than looking at static plots, so that's really useful. Now, that was a temperature, a heat flux that was dependent on Cartesian and temperatures of the surface. Now, we might have a slightly different relationship between our heat flux and our. So instead of doing a Cartesian and temperature dependent heat flux, we have a heat flux that is actually dependent on the surface temperature, but also the time of our simulation. Now, we could simply create a new field that has as the dependent domain the heat flux value, and as the independent domain, we would have temperature and time. Temperature and time. And thus we get a Excel sheet that has 3 columns that we could fill out as temperature, time, and heat flux. Now, sometimes that's not quite how we have our data set up. Maybe it might be, we could do some Excel matching, mismatching, and fitting all the data into one table. But sometimes it's a lot easier to simply create what we call a table of fields, a table that references other tables. So, for example, I have at 100 degrees Celsius, I have this type of relationship for my heat flux versus time. I have a linear increase. That is slightly different to at when my surface temperature is at 50 or at 60. Now, we could merge these into one field like I just showed, but instead what I'm going to use here is a table of fields. And the way it works is we're still using the same dependent domain, that is heat flux, and independent domain being temperature and time. Temperature and time. And here, however, instead of being 3 columns, we have the temperature and then a field. So we'll reuse those 3 fields I already have for heat flux versus time. So at 50 C, I have that temp 50 field. At 60, I have the temp 60. And finally at 100, I have that final table. And we could directly apply that table in our heat flux boundary condition that we had before. So once again, using the FD function, we simply need to change the name of the field being called to table of fields, which is the table of fields that we just created. Now, if I wanted to evaluate that field and see what kind of heat flux I would get at temperature of 100 C at a time of 0 seconds, if I type this in like this, I actually can get the constant that gets evaluated. So right now, this flux would be a constant flux of 10 watts per millimeter squared at 100 C and at time 0. If I change that to time 100, for example, we would get a new value being 210 watts per millimeter squared. So that's another way to validate that our table of fields got inputted correctly. Now, this would work super well. It would evaluate through time, but let's assume that this field is coming from, this heat flux actually, is coming from a motor being started. Now, I don't want this motor to start at time 0 in my simulation. So one way to implement that logic is to directly add a if-else statement in this dialog. So without having to write a user subroutine, we can add logic to this heat load. we can simply say, for example, if time is smaller than 10 seconds, our engine is still off. The heat flux should be 0. But once the time goes over 10 seconds, I want the heat flux to start and use the table of fields that we generated just before that. And so this is essentially coding, but directly in Simcenter without having to relearn Fortran. Now, I could run this, and I actually did run this model before, and just to save some time. And what I want to show you in the results here is the heat load. So if we look at the heat load at time 0 here, we see that there's no heat load on the spacecraft because our time is lower than 10 seconds. However, as I moved forward in time, and you can see the time here, 2.5 seconds, 5 seconds, 7.5 seconds. When I reach 10 seconds, that's when my flux starts being active. And if we create a graph of the maximum heat load on the model versus time, we can see that also graphically. So before 10 seconds, my heat flux is 0. At 10 seconds, my heat flux turns on with the field, and then it will vary through time as the field that I put in varies. So that is what I wanted to show to you today. What we saw is that we were able to apply 3D fields, 2D fields, and 4D fields very easily directly in the interface for Simcenter without any coding or user subroutines or custom input cards into the solver. We saved a lot by not doing that. We could graphically and visually check our data. We didn't have to run the model before doing that. We were able to look at the different interpolation schemes and their effect on the data. This minimizes errors. As you can see, it's quite easy. Case in point, me typing in that formula wrong. We also imported comma-separated value files or text files directly into the software. So the data could come from pretty much any source. And it's a very reliable process because of all that checking, because of we are using quality assured interpolation schemes directly coming from Simcenter 3D itself. So just before we finish, let's do a quick summary of what we saw. We saw that Simcenter 3D has a long and successful CAE heritage going back many years. We have a very wide range of applications coming from acquisitions recently, but also just through growth, natural growth. Now, I didn't touch too much on this, but do remember that inside of Simcenter 3D, and what I was showing is Simcenter 3D, the thermal solver, or Space Systems Thermal, which has some of the best in-class geometry editing and associative CAE modeling, because we are working from NX as a CAD tool. We have advanced physics, advanced radiation models for orbital heating and solar heating, non-gray radiation, as well as ray tracing. We do have multi-physics capabilities, so for thermal and flow analysis. We do take advantage of high-performance computing, so you can run your V-factor calculations as well as your thermal model in parallel. We saw some of the very good pre-processing tools and a little bit about the post-processing that is embedded inside Simcenter. Also, we have full integration with the Simcenter, which is our PLM software that can manage your data from CAD to analysis. And to summarize one last time what we saw today regarding the boundary condition mapping of 3D data, we saw that it was directly integrated in the UI. You didn't have any custom code to write, no input cards to do in a text file. We saw the many ways we could graphically check the data, which really reduces any sources of errors there. And it's compatible with pretty much any tool that can output a CSV file or a text file, and you can import that data directly into Simcenter 3D. Before we go to some questions, I did want to mention that we have a few more papers and presentations today that were done and use Simcenter 3D Space Systems Thermal. So this afternoon, we have a passive thermal paper that one of my colleagues is presenting, where we did thermal design correlation using Simcenter 3D, 2 TVAC test data of a lunar rover prototype that we worked on with Canadensis and the Canadian Space Agency. We also have at 3 o'clock Central Time interdisciplinary paper session where we actually look at optimization and surrogate thermal models using Simcenter 3D and TFAWS. And also we're doing a coupled thermal structural analysis. So we're running both in conjunction in an optimization tool. So that one should be very interesting. It's at 3 p.m. this afternoon. And right after that, in the same session, we have another session where we talk about some of the strategies that we looked into for creating reduced order models using machine learning algorithms, as well as the HEAT software, which is an optimization tool that is part of the Siemens portfolio. So that is all I had to present today. So hopefully it was interesting and everyone learned something. If you have any questions, do put them in the chat, and we'll go through them now.